So hello everyone. As a last talker of this session, I managed to do not overlap the same thing, but it's difficult. but, I'm Yusuke Fujita from Hitachi, Japan. I will introduce. I'm sorry. Wow. I will introduce our submitted system for this CHiME challenge. First, I introduced my background. Hitachi is developing a humanoid robot named MS3 for customer service, like airport and station and bank in Japan. So distant ASL around 1 meter is required. So noise robustness in this rare field is crucial. So that's why we participated in the CHiME 3 challenge. So we developed a local Gaussian model-based source separation. This works well with DNN-based SL. So we also developed a discriminative system combination that outperforms a classical lower method. However, the data augmentation technique, a speaker adaptation technique, and LLM examined by top teams in CHiME 3 have not been applied. We followed these state-of-the-art techniques and updated our system for this CHiME 4 challenge. This is our contributions for this challenge. First one is a local Gaussian model-based source separation. This is based on a multi-channel linear filter. And this output is utilized for acoustic modeling and front-end speech enhancement. Moreover, introducing a semi-stationarity constraint to non-target sources that improves front-end speech enhancement. The second one is some other people use unsupervised deep neural network adaptation by retraining approach. Using a conservative setting of training parameter works well. And finally, the phonetically oriented system combination is developed. So this is a multiple one-best sentence are combined, considering phonetic similarity that improves the system combination performance. So first, brief introduction to local Gaussian modeling. But first formula is just in the SDFT. So the number of microphone is M. So local Gaussian model proposed by Duong 2010. So input signal is decomposed into the summation of spatial image of each source. This is a multi-channel signal. So this spatial image is modeled by single Gaussian, the zero mean and this covariance. This covariance is factored by activity scorer and spatial correlation matrix. And then this spatial image is calculated using multi-channel linear filter, this formula. And this V is activity, and this large V is spatial correlation matrix. These two are estimated via multi-channel linear filter iteratively using AEM algorithm. So here is comparing with beamforming. Beamforming outputs the single channel output signal. On the other hand, multi-channel linear filter outputs multi-channel signal. So how do we utilize the multi-channel output signal C? So our approach is, one is data augmentation, and the second is a preprocessor for beamforming. Okay, so this is our approach to data augmentation for acoustic modeling. So very baseline is using only fifth microphone. And our CHiME 3 system using fifth microphone in this enhancement signal. So entities CHiME 3 system use a multi-microphone training That's all micro signal are fed into acoustic model training. So here is our contribution. So multi-channel output signal, this enhanced 6-channel signal is all fed into acoustic model training. So this further improves the word error rate for real test set. And then moreover, not only using the enhanced signal, but also using an input unprocessed signal. So total 12-channel signal is all fed into the acoustic modeling. Acoustic model training. So this further improves the results. And the second utilization of LGM is preprocessor for beamforming. So output of multi-channel signal has 6 channels that hold spatial information. So any beamforming technique can be applied. So we use the cascading of LGM and baseline beamforming. So this technique further improves the word error rate. And here we update the blind source separation and target source selection is updated. In our previous system in CHiME 3, the target source the speech is selected using SRP flat on front direction. This uses a geometry on microphone. So, but sometimes it fails due to permutation errors and how to hold a tablet device. So this is not so robust. So we changed this target selection algorithm, introducing permutation-free modification of LGM. So, so what we modified is introducing semi-stationary constraints to noise sources. Target source, so speech, is not modified. It's the same as original LGM framework. But non-target sources, activity is modified. How modified? Using moving average filter applied to original activity. So like that. So applying this moving average filter in each EM iteration of multi-channel filter, so target source that is most active source is extracted onto C0, zeroth channel. I'm sorry, zero source index. So we no longer select the target source using SLP flat. This makes a robustness. The word error rate is reduced. Okay. So second contribution is unsupervised network adaptation. This is standard, almost a standard technique, by examined so in the past CHiME challenge. So concerns about retraining of DNN. We think this kind of thing. Unsupervised adaptation phase when the large number of DNN parameters are adapted, that is reported by DAO in 2012. But our system is almost the baseline DNN. The parameter, number of parameter is 32 mega. So in our case, it's medium size. So we did not try any parameter reduction techniques such as a low rank approximation or partial layer adaptation. Adaptation of entire network works successfully. And hyperparameter used in this training phase is not appropriate for adaptation. So we choose 3 hyperparameters: learning rate and mini batch size and the number of iterations. Here also L2 penalty, also called weight decay, may be a good option, but we didn't try it due to time consideration. So this is a result of unsupervised network adaptation. First, any hyperparameters reduce the word error rate from no adaptation results. And small running rate around 0.0004 is good performance. And early stopping, it means iteration is only 1 or 2, is good performance. And finally, the best development average word error rate is achieved using 12,000 frames of mini batch. So, but almost the same performance is achieved using 256. So we can't conclude that large mini batch is good or not. So the last part is phonetically oriented system combination. And this is combination of one best results from various systems. Like Rover method, word alignment among multiple sentences is important. But here, this is an example. Conventional word alignment sometimes fail in the time alignment. This is there, and this is another there. So this makes error in the system combination. So Lewis proposed a phonetically oriented alignment. We use this alignment to improve the system combination. Okay, the feature vector for system combination is this in this slide, using a confidence score and co-occurrence. This is whether two hypotheses are identical or not. This is binary vector. And null is whether a chunk is deleted or not. So using this feature vector, logistic regression model are trained using development set. This is a result of system combination. We used 12 backend, including baseline and data augmented models and speaker adapted models. And each backend models, we use the 2 front-end speech enhancement. One is baseline beamform it, and other one is LGM preprocessed beamforming. So using 24 recognizer combination without phonetically oriented word alignment, the result is better than best single recognizer. And with phonetically oriented word alignment, the word error is slightly reduced. So this 4.68% is our submitted system for 6-channel track. This is summary of our experimental evaluations. So LGM-based system reduced word error rate is all the tracks, but especially on the 6 tracks, 32.1% relative improvement. And speaker adaptation is also effective when base word error rate is low, because the supervision is more confident. So finally, the system combination reduces word error rate on all tracks, but relative improvement differs on the tracks. I don't know why the 2-channel track, the improvement is small. So conclude, we developed a local Gaussian model-based source separation. And marginal winner filter is useful and achieved up to 32.1% gain from baseline. A second, unsupervised deep neural network adaptation is examined. And this is also works well and achieved up to 28% gain on 6-channel track. And finally, phonetically oriented system combination is examined. achieve up to 50.8% gain on 6-channel clock. So that's our future work. So cross-adaptation or community-based adaptation for speaker adaptation is it gives will give the better performance because supervision from other system is will be good, maybe good, not as self-adaptation. And noise environment adaptation is more desired than speaker adaptation in our field, the robots application. Speaker in front of robots changes rapidly, but the noise environment is relatively fixed. So the noise adaptation is would be feasible. So last, deep learning-based marginal winner filter and its joint training of the filter and acoustic model is just I want to study. Many studies on this field are found in interspeech, last interspeech, and today a lot of presentation using deep learning. So I want to do it. So that's all.
I have two questions. One is, did you compare your adaptation approach also to, for example, using CMLR or FMLR?
No, FMLR is used in baseline feature extraction. We do unsupervised adaptation using the baseline feature. So FMLR and unsupervised model adaptation is also together used. This
okay, so it's
improves
additive.
the result.
It's additive, therefore. Okay. And the other question is, you're using a huge number of systems to combine.
Yes.
I suppose there at some point you would see some convergence. Did you analyze that? So once you add more and more systems, at some point I would expect that you don't really get gains from using even more systems. So did you analyze that?
I think as our classical Rover method will fail using a lot of combination, a lot of recognizers, because somewhat bad recognizer tend to reduce the performance. But here is a discriminative method. So word selection algorithm is trained discriminatively. So this is why we can use a lot of recognizers.
But like, did you check, like, if you would only take 6 or 12 of the systems, what would you get?
Yeah, we did the experiment on only baseline systems. This 4 system, maybe 4 system. Improvement is small. Only using baseline. Right? As a developer of system combination.
I'm a second author of this presentation. We checked when we change the number of the recognizer to combine. Honestly speaking, the best one is when we combine 16 systems. So 16. 10 plus 6, yeah. So this is 24, but so it is slightly bad from the best one, but the difference is just 0.1% or a little bit, yeah.
Any other question?
So in your first slide that you guys showed that Hitachi has a microphone narrator, this kind of application. I'm curious, this kind of CHiME reader techniques are also the effective of your this kind of application, or there some techniques are not applicable, or I just want to know how much the technique developed here can also be used to this kind of other domain.
So actually, speech enhancement using our approach, this is an iterative function. This is not feasible because our approach costs very time consuming. But as acoustic model is easy to use in this robot field, and the speaker adaptation, model-based adaptation is cannot be used, I think. But so as I said in the future work, there's unsupervised or so adaptation to noise or environmental adaptation. So continuously is more and more feasible. So this kind of technique can be used rapidly for the robot system, I think.
Okay, let's thank the speaker again.